Welcome everybody to our roundtable tonight. Tonight we have a very special guest. We have Kathy Eblin-Shaw with us from Malmark. She is the Director of Sales and Marketing with Malmark, and she is also with the Westminster Choir College. And before I turn it over to Kathy, if you could drop in the chat where you're from, who you're with, that'd be wonderful. And I will turn it over to Kathy. And Kathy, I have you muted, so just make sure you unmute yourself.
I did. Okay, thank you. Welcome, everyone. It's so great to see so many of you on a Monday evening. I'm here at Malmark in Plumsteadville, Pennsylvania, which is located about an hour north of Philadelphia and 2 hours southwest of New York City. So if you are coming through once all this post-COVID travel begins again, please stop by and visit us. So tonight I'm sharing a video with you about production at Malmark. I'm going to be adding some commentary, but just to let you know where I'm in the conference room at Malmark, and behind me on the wall are all of the patents that Mr. Malta created for both handbells and choir chimes and cymbals. And his first patent is hanging there too, which is the patent because he designed the Schulmerich bell as well. And as I love to get the truth out, and I'd just like to give you a little bit of history. In 1963, Jacob Malta worked for Schulmerich and he designed the Schulmerich bell. And in 1969, Schulmerich was sold to another man by the name of Ken McGrath. So George Schulmerich sold his company. And at the time, Mr. Malta was in his 50s, late 50s. And Mr. McGrath thought that Mr. Malta was getting a little old to be the chief engineer. So it was very, if you all can think back, I see a lot of older folks like me, folks of my generation on the screen, but that's what our parents did in the 60s and 70s. When 65 came, they retired. And so Mr. McGrath was worried that all his eggs were in one basket of his chief engineer, Jake Malta, and he suggested that maybe Mr. Malta should think about retiring soon. So Mr. Malta did leave Schulmerich. And he just went out and did other designs. He was designing, we're here in Bucks County and there are a lot of horse farms. He was working on horse trailers. He designed the ringer and the princess telephone. So, which is kind of uncanny with the bell relation. But he really he fell in love with handbells and the challenge of handbells. So he decided that he would start his own company. So that meant that he had to redesign a bell, make a new design. He had to figure out how he could do it competitively, pricing wise. And so he took about 3 years and worked at a card table in his living room and basically created Malmark. In late 1973, it was right before they were ready to incorporate. He was driving in his car. It was December. It was his wife's birthday. And he knew he had to come up with a name for his company. And he had just bought his wife a birthday card, a Hallmark card, which is, the symbol of quality is what a hallmark is. And so he thought, Hallmark, Malmark, I'll go with Malmark. In a couple of months, he invited then the sales director at Schulmerich, who he worked with, Willard Markey, to join him at Malmark. And so it kind of was nice that it was Malta and Markey and Malmark, but actually the name came from a Hallmark card. So that's the little history there. So there really was not a war back then. He got along well with Mr. Schulmerich. It was just an age thing. But I will say that Mr. Malta worked here at Malmark 7 days a week. I never knew him to take a vacation. I've been working, at Malmark since 1985. And so he just loved what he did, and he was here at Malmark. And so today I put together a video that was filmed by one of our Pennsylvania networks, and I pared it down a bit, but it's actually Mr. Malta giving you the tour of Malmark. So when Sarah asked me to join the session tonight, I asked if it could be this week because it's Mr. Malta's 102nd birthday, or the celebration of his birthday on June 13th. So before I get started with the video, we're going to start right in our shop here, in our machine shop, which is the first step in manufacturing handbells. But I wanted to share with you that this is where we start with the bell. Here at Malmark, we do not have our own foundry. We can't pour our own metal. It's a zoning issue. And so we have two foundry sources, one about an hour north of here in the Lehigh Valley, and one about an hour east of here in New Jersey. So that's where we get our bronze castings. The castings come to us like this. They look very rough because they're what we call a sand mold casting, meaning that there's an indentation put into cold sand, cold wet sand, and the metal is poured into the sand, and that's how the casting is created. The bell is 2/3 thicker than it normally what it would be. This is an A5. The reason for that, with a sand mold process, it is believed that all of any waste in the metal or any contaminants in the metal would go to the surface. So the idea is when you use a sand mold that you're going to go to the heart of the casting, and that's where the best metal is, and that's where the metal settles in the mold. The other thing is that the casting is 2/3 thicker because as we remove metal from the casting, that's how we are lowering the pitch and we tune. So our craftsmen can never take too much metal off the casting because it's a reject then. Here at Malmark, we reject 40% of the bells that we make. 40% for two reasons: sound quality. Bells are just like human voices. Some are straight tone, some have a lovely singing voice, and some have a lot of vibrato. We never want to use those bells with a lot of vibrato because they don't blend in the set, just like sometimes sopranos and tenors don't blend with your singing choir. Okay, so usually our rejects, a lot of our rejects are on the high end in the 7s because of that. But the good thing about it too is not every bell is a reject, even though it has vibrato, because we can revoice the bell. We can turn the casting and find a new strike point. And sometimes you'll have a point that has a lot of vibrato and you just turn it 1/8 of an inch around the casting and you could find a beautiful straight tone. So that's the beauty of our bell. You just loosen the main assembly screw and rotate the casting, and oftentimes you can find a more beautiful response point on the casting. So I am going to start this video before we run out of time. I thought I would stop in between rooms in case you had any questions, and I'll ask Sarah if she'll help me with that as we're going.
We've now entered the machine shop, and this lathe on my left is being operated to turn the OD, the outside diameter. He's just completed one cut, backing up the carriage. Oh, he's setting up. We catch this fellow in the midst of setting up the machine. And that's the stopping device, the device that stops the carriage's forward movement so it doesn't go too far. So he's tightening up this stop block. so it can go a little bit further on the next cut. What we have here is a cutting tool on the end of this tool holder, and it's coming in. It's going to engage the stem or tang on the bell any moment now and start to remove metal somewhere along the line. This is a sand casting. The bell is made from a sand casting, and they are never uniform due to the fact that the sand in the mold compresses unevenly. So during the first cuts, it may cut in certain areas and may not cut in those areas on the next bell. This is now beginning to cut on the tang. This device back here, this portion, is a hydraulic tracer. It's separate. It's not part of the lathe initially. And it contains a hydraulic cylinder here, which is controlled by this stylus. And if you can get a shot of that stylus, you'll notice it has a large diameter, which is now in contact with this template. And then the diameter reduces as it goes up. And as he's moving along, if you notice here, this sheet metal part this is the template, and there you can see the shape of the outside of the bell. Here's the top of it, and here's the side, and here's the bell at the lip. Every bell that we turn has to have an outside template, such as this is, for outside machining, and then an inside template, which I'll show you in a little bit here, for machining the inside of the bell. Back here, for example, is a very large fixture for holding extremely large bells. This weighs a few hundred pounds, and it contains a chuck with a fixture that we developed and built for holding the bell to prevent vibration while it's being machined. We have a number of these for different sizes of bells. Behind you is a very important part of this operation, and here we have our masters. All of these are castings which I developed over the years. Many thousands of hours are involved in these. And these are the masters for every bell that we make, and the machinists use these. They make reference to the readings that I've written on them, and this is what they have to machine production bells to, and they use these to set their machines up with. So all of these are extremely valuable to us because they all represent hundreds of hours each in development. Next to those is a tracing table. This is a finely ground surface of marble. And in this operation, we can take and actually see, I just locked the bell up, we can actually read on a sheet of tracing paper the shape of the finished bell. There's a very fine tip on this, and we can run this down the inside of the bell. There is a ballpoint pen down in there, and we can back it out and move over and then do the outside of the bell on all four sides. And what we get from this is an actual tracing of the shape. I don't know if you can pick this up, but there is a tracing of a bell of about that size. So that we always know roughly how thick or how thin we are, which we must know as we go along. Well, we can move on down here, if you will. And Is this set up? I just turned this tracer on, push the green lighted button here, and this is another outside turning machine, and we're on the first cut on this casting. This tracer is automatic and will back in and out 4 times. On this casting, it will cut 4 times. After the 4th cut, it will have its finished final outside dimension. Again, back there is a stylus following a template, just as we saw in the first large machine. While that's turning, if you like, you can observe this fellow over here. He just tuned the inside, tuned on the inside of a bell. He's reading up here on 2 instruments, 2 different tones that he is controlling in the bell, moving in relationship to each other. Now, what he did was to strike the bell while it was in the fixture, and there are 2 microphones. And these 2 microphones are connected to these instruments and feed into the inputs, and the tonal vibrations they pick up in the bell are fed into the instruments, and he reads those just as we saw the fellow doing crotales, reads those frequencies in the windows. In the meanwhile, this tracer completed its first cut and has come back in again about 1/3 of the way through its second cut. And in several seconds, it'll complete this cut and it will watch the tracer reverse itself automatically and then come back in. Now reverse, retract, and now come back in and advance again. Based on the position on that white cam back there, it's on its 3rd cut now. And as you can see, on its 2nd cut, it completely removed the outer skin of the casting this time. There are times when you go through 3 cuts before it will do that. Again, it's because of the fact that sand castings are never uniform with respect to each other. Move on. This fellow is again, he is setting up for a new bell. He's got his fingers holding a template. He's positioning the template against the stylus. And then he's got a hex wrench. He's going to put a spacer on it first. Now he's going to tighten the set screws using a hex wrench, hex socket wrench. Now he's doing exactly what I described over at the tracing table. He's got a master bell, one of those bells from the masters over there, and he is setting his cutting tool up to follow the profile, and he makes adjustments so that he can achieve that by turning these dials. This is the end dial. Turning that, he's turning it in right now, so he has to get in closer. And this is the side dial, which he will control how close the tool gets to the side of the bell. Now he's cranking the tracer through by hand. He'll disengage that crank afterwards when he's all set up, and it'll run automatically with a clutch connection. Now he is adjusting a rather interesting device. This portion here is a fixture which clamps the bell, and it's adjustable through a fairly large number of different sizes merely by loosening the set screws that he was just tightening and moving these posts in and out, so he can move the position of that with respect to the size of the bell. Now he's taking a measurement to see if he's adjusted this uniformly. Over here is a bell that just finished in the meanwhile. This is located behind him. Each man operates two lathes. He can operate an outside turning lathe, and merely by, as I'm doing now, removing the finished casting, putting another one on, it's ready to go. Here's a green light which tells me the tracer is in its retracted #1 position. So all I need to do is to turn the lathe back on, it's running, and hit the button. Now this is what he does. At this point he can turn his back to this machine probably for about 15 minutes time, which this will take to go through 4 cuts. And while it's doing that, he's over here tuning on my left and completing the inside of a bell. How you doing? We've worked our way down the row of lathes, and if you noticed, we started at where we started, rather, we start with big bells and we work our way down. Here's where we do the smallest bells, the bells of high frequency. Now he's going to strike the bell with a handheld striker. He adjusts the dial to the point where the rolling bar pattern will stop, as we saw previously. And you notice that as he turns the bell, the chuck the pattern begins to roll. That's because the frequency varies around the diameter of the bell for several reasons, which I'll discuss a little bit later. Now he's ready to start tuning another one now. Over here on these shelves, you'll find this of interest. You've seen on that first machine, we had a casting that was probably about 14, 15 inches in diameter being machined. And here truly is a bell. This is one of our smallest bells, just the size of a thimble. This portion, of course, which is needed to hold it in the machine, gets removed. So the bell is from bell size from here down. And that bell is tuned, and it's an E9. That's way off the end of the piano keyboard, way above it. So gives you an idea of the range of bells that Malmark makes. So I guess we're ready now to go on into another department.
So, friends, I just wanted to mention a couple of things, just to point out that may have been missed in because I started the tour in the middle. First of all, most handbells are tuned to 2 pitches. The fundamental, or the pitch on the handle, comes from the lip area. And that's why you saw 2 microphones on the strobe, because one mic was checking the tuning of the fundamental pitch. And then the 12th, or it's a perfect 5th, but an octave and a half above. It's not a perfect 5th, but it's a 12th. So for instance, this bell is a G4. So the G comes near the lip. And then a D6 sounds at the top, at the waist. So we have to make sure that the G4 is in tune, as well as the D6 when we are machining. The second thing is that I guess you notice that all of the tuning is done on the inside of the casting while it's being cut. And it takes a good hour to an hour and a half to set up a machine. So we always run castings in quantity. In the day, it used to be 100 at a time. It may be, depending on the bell, it may be 25 to 50 now that we run at one time. And just one thing on the tracing table, if you should have a casting that is cracked and you send it in to us for warranty consideration, that's what we do with your bell. We trace it to make sure that there wasn't a thin point on the casting. So we were able to see if it was a good casting that may have cracked due to mallets, which is always usually easy to see because the metal is pushed in, or perhaps a martellato is another prominent reason why a casting would crack. So we always do trace the casting to make sure that we didn't send you a casting that was too thin. Very quickly, are there any questions? I'll let Sarah run that.
Yes, there were a few in the chat. What year was the video put together?
1997.
And has there been any additional automation technology or safety measures added since then?
Yes, of course. Safety glasses. You saw some of the guys wearing ear protection. We're a little bit more. OSHA has, we do follow OSHA precautions, so we're a little bit more careful about that. Of course, right now during COVID, we're all wearing masks still. We now have 2 CNC lathes, which are computer operated. We use those for the outside turning of the castings, but never the inside tuning. That is just, it's an art form. It's a craft.
And you were saying how many bells you produced on each setting. How many total bells do you produce in a day?
How many? Oh, it depends on the size. So for instance, if we're turning an aluminum bell, that one bell could take several days. So it all depends what we're running. Yeah, some days we'll have 200 bells come out of the polishing room, and other days we'll have 25. It just depends what's going on.
And have you reopened to physical tours yet?
We have not. Probably in the fall we will.
Okay, that's all for the moment. Keep asking questions as we go along, but that's it for the moment.
Okay, and I will resume. Sarah, shout out if I don't do this correctly, please.
Here, by the way, we don't throw away those turnings, those chips. They're extremely valuable. We have to pay the foundry for castings roughly in the area of $7 to $8 a pound. We buy ingot, which we furnish to them at market price, which can be anywhere from, in the course of a year, from $1.80 to $2.25 or more a pound. So we save all these chips, and we accumulate 30 to 40,000 pounds at a time. And then a truck will come in from Chicago, where the smelter is located, and we'll pick up the entire shipment, take it to Chicago, where it's reprocessed, melted down in furnaces, and the alloys are checked and corrected, the alloy content. And then it's poured into ingot, into bars, which they return to us, which we then distribute to the foundries. Now, we're now in the polishing department, sanding and polishing, and along this row of machines on these benches, we've got 6 different operations or operators working as a rule, and they are doing the major part of the sanding on the inside of the bell. He just finished sanding, and what he's done now is get a flexible shaft machine. There's a bob on the end of it, a polishing bob, and the flexible shaft is turning at about 3,450 revolutions per minute, and the bell is turning at 3,450 revolutions per minute in the opposite direction. So we've got over 7,000 RPM working for us in producing a high polish, as you can see on the inside of that bell. Now that's developing a great deal of friction and a great deal of heat, so it's going to be necessary for him to read the frequency before he passes on that bell on for outside polishing. So he's got to allow that bell to cool before it's read. So his next step will be to get another casting and perform the same operations to it. The operations that he had performed, if you'll look here, were to use these different size grits. This is a coarse grit. These two happen to be empty right now at this position. This is a very fine grit. And what we do is we take and use a backup belt strip, tear it off, and then we proceed to polish the inside of the, oh, this is a hot one. Very hot. Yep. Grabbed the wrong one. This is not yet polished. But they will then polish with these different grits the inside of the bell, remove all the tool marks, and they'll make 1 or 2 passes on the outside to make it easier for the outside polishing operation. But the purpose that these fellows are attempting to achieve is to get all the tooling marks off the inside of the bell, and to bring it down, bring the bell down. That chart is almost unreadable now, but they know what the notes are. They can look at a note and find the readings that should be, that the bell should read when they're on there. Here's some better charts that they're apparently referring to now on this wall. And they can pick out the musical note that they're working on. For example, G5, where I have my finger, the fundamental tone, this is the heading fundamental, should read between 0 and +10. Well, what they attempt to achieve is a +5, which would be exactly on frequency. And then that's the fundamental. Up here's the 12th. And so look across, and the 12th tone for a G5 is a D7. And that should read between +12 and +22. A perfect position for that would be 5 cents in between, or 17 cents, which would be the midpoint. And that's what they attempt to achieve all the way through. Each of those fellas is doing a different bell. They have to check the readings on those bells as they go along, and they'll bring 20 bells over to those instruments there and the charts. And check them probably 3 and 4 times before they're done. Now he's doing a small bell which he can finish rather quickly. What we have here is an outside polishing operation. After the bells have been done on the insides, they're brought over here once they've all been read and checked on those instruments against those charts, of course. And what he's doing is he is holding a bell and rotating it by means of handles that we have provided, which clamp the bell between. And he's holding it against a high-speed polishing wheel. He just applied Tripoli compound, which is a compound from which jeweler's polish is ultimately made. This is more coarse. And he's removing all the machining and tooling marks from the outside of the bell. Now, he goes round and round the entire surface, and when he's gone all the way around it, he's going to inspect it visually to look for any lines or blemishes that he hasn't polished over. Now, when he is finished with the outside of that, he's going to refer to his chart, which is here, which will tell him what that bell now should read at this point. And if it doesn't read that, he's got to repolish it. We purposely leave the bells higher in pitch, slightly thicker. The thicker, the higher, until we get down to the desired frequency. Now on this side of this buffing lathe is another wheel, and this is the buffing wheel. It is not as hard as the polishing wheel. It's loose sewn, very soft. We apply a coloring compound, it's a white bar instead of a red bar, to this wheel, and this will remove the residual Tripoli compound from the bell and leave a high luster on the bell, a high polish. Okay.
Okay, a couple of comments. First of all, the chips that you see, 2/3 of the chips are removed from the castings. That was something new when Mr. Malta designed Malmark and its manufacturing processes. It was normal that you would use a coolant in cutting the castings, but he chose not to use a coolant so that he could recycle the bronze. If he used a coolant, then the bronze couldn't be recycled and it would just be waste. And he was trying to keep costs down because most of our customers are not-for-profit organizations. The other thing I wanted to mention is the polishing wheel, the buffing wheel. Those are cotton wheels, so they're very, very soft. They look like they're hard. And also the bob at the end of the polishing wand is also cotton. And when the castings are in the machine room, they're left to be a little bit higher, a little sharp, because when they go over to the polishing room, they again, the polish will be, I'm sorry, the polishing procedure will cause more metal to be removed from the casting, lowering the pitch again. And the numbers that the craftsmen are reading off the charts are the cents for the tuning. So if a C5 reads at 100 cents or 1/100th of a semitone, so basically between a C5 and a C#5, there are 100 small degradations. We call them cents. And so that is telling us what cents the bell should be tuned at. So the higher the pitch, the higher the cents, because we do stretch tune like piano and organ tuners. Whoa, what's going on here? Okay, Sarah, any questions?
There was one, but he said Jake answered his question 15 seconds after he asked it. So
Okay, I don't know what's going on, why my email popped up here. We're just gonna close that. Okay, here we go.
We are now in the final assembly department. This is where the castings from the polishing department are brought, and if you will look along these tables, you can see a large number of, on this side, small castings that right now this lady is beginning to hand polish them to remove the residual polish from the automatic or the operation done in the polishing department. And over on this side, you'll notice again some larger ones, and here are some that have been put together already. That is, these are the castings that were brought in from behind us in the polishing department. And notice that we have bins here, and in this bin, for example, we have a clapper assembly, or a number of them, and here's the handle, and it is for a B5 bell, and here's a handguard for the B5 bell. So these are the parts that will be assembled to the casting that is marked B5, brought in from the polishing department. So they'll bring B5 castings in when they are going to assemble and use these parts on them. The next one is C6, where we go up and down the musical scale here, and that's how it's done. She's now, what are you doing, Lori? What note is this? E5, right. And this young lady is doing E5s right now, putting all the parts together. And she'll follow up by putting handguards on top, and then assemble the handle, and then fasten all parts together with just one main assembly screw through the, there is a block here, a handle block, and a hole in there, and she'll put a main assembly screw through, and it will assemble the entire bell, hold it together. Now I think I ought to demonstrate a bell for you to show you, let you hear what a clapper does to the sound of the bell, the variation that we can get from a Here's this is it's an F sharp 4, and I'll just demonstrate the sound effect that our Malmark clapper produces. Now I just struck with a felted portion of the clapper in the striking plane, produced a soft strike. Now with my fingers I turned it. Now the felt is no longer in the striking plane. The clapper moves in a straight line in this direction. And now I've lined up a slotted portion, or a lobe on the clapper, and I've increased the intensity, and it sounds like it's a different frequency, but I've just changed the tonal color. Now I change to the third position, and even more of a brilliant effect results. So we'll go from a soft to a medium brilliant to a high brilliancy. So we change the tonal color very quickly. Can be changed during the course of playing a musical selection, and composers do write their music around that feature in our bells. Now these bells have been assembled, and they've gone through a step between the assembly that we saw a little bit ago, where the young lady was putting together the handle and clappers onto a casting. They're all brought over here. And this is a voicing room. And here the bells are not only rechecked as to frequencies, but they're also checked for mechanical defects, and also checked orally. In other words, they are listened to. And even though the frequencies may be tuned correctly, the sound quality may not be acceptable. And each time she is striking that bell, each time her left hand touches it, she's moving the casting in a circular fashion, just a very small amount. She just changed the clapper position, by the way, from soft to medium, to excite a higher frequency, which she's reading on the scope on the right. Now she goes back and reads the fundamental frequency with the felted position, and she was selecting and listening as she was doing that to the best point of response on the bell, and she located it. And now she's going to go ahead and she's going to put a permanent scribe mark inside the bell in alignment with the plane in which the clapper moves. And if in the future it's necessary to disassemble the bell to clean and polish or do whatever, it can be reassembled to that line again, which is the point of best response. As she's readjusting, we have at the bottom of the clapper assembly, there are restraining springs which adjust the restraint on polyurethane springs which hold the clapper away from the bell after it's been struck. The springs permit the clapper to override and strike the bell on the forward stroke, but then hold the clapper away and allow the bell vibrations to continue afterward. Okay, this young lady has bells arranged up here which demonstrate the various defects or porosities and causes for rejection, whatever. This one is especially interesting because, as you can see, it's got a pretty substantial hole in it. And I think most of us will remember the earthquake in Kobe, Japan. And this was in the earthquake, and this was one of some that we replaced for a customer who had the misfortune to be in that earthquake. Now from here, I said that she checks these orally in addition to checking them on the instruments. And interestingly, while the tuning will be correct because they've been checked and rechecked again all the way through the process. She will reject a pretty large number, probably about 20% of them, for sound quality defects. Now she just finished another, and she's going to permanently scribe it. Now, as I said, she gets about 20% of them that will be rejected for tonal quality or lack of it. And those that she rejects, she sets aside, and they've got to then go out to the final assembly tables and be disassembled. You know, while she had that on the hard position, there was an audible beat, a wow, wow, wow effect, and that's what she's listening to and trying to locate a spot around the bell which produces a minimum of that, which she just did. And now she's ready to scribe that one. She uses different color coding, which is, you know, proprietary to us. She has different colored markers there, and the markers, depending on the color and the code that she puts on there, it tells the people in final assembly whether that bell is, let's say, a very clean-sounding bell, very little in the way of beats and wows, or whether it's got some moderate beats and wows, or whether it's got substantial beats and wows. All right, now in the voicing room, I commented about the fact that we have about 20% reject rate for sound quality, that is for beats and wows. This is in addition to a fairly substantial amount of rejects for surface defects, porosity. But here, on both sides here of this aisle, we have bells that have been completely assembled out in final assembly, brought into the voicing departments. And there is another voicing room here, by the way. And they've been checked and found lacking. In other words, there are excessive beats and wows in them. They will not fit in with the standards of quality that we require in our bells. So these are all rejects, absolutely, with all the cost and work and done to them, turning, tuning, polishing, and voicing. This is where, unfortunately, an awful lot of bells end up. And we have thousands here, obviously, and in our rear building we have thousands more, many, many thousands of them.
Go ahead.
All right, we're now in subassembly, and subassembly is on the opposite side of final assembly from where we just came, and beyond the, on the other side of it, if you recall, final assembly was the polishing department. So materials funnel in from both sides into final assembly. Now here are small parts that make up different bells that we make, and this is a heavy bushing, a weight that we need on the end of a clapper in order to produce the right impact force. And this is a bushing with a nylon insert which permits us to rotate that clapper, turn it from one position to another without having the a clicking or noise develop. These are all parts which go into various clapper assemblies. Here's a bushing of another size. Here's a spacer washer. This is a restraining spring. We talked about restraining spring. This is one for a large bell. It fastens to the clapper spring plate. We'll see that in a minute. And it restrains the clapper action, allowing the clapper to go over, strike the bell, and then bounce back and be held away. This is a spacer bushing used in large clappers. And here's a variety of fasteners, screws of different sizes, lock washers, and spacers. Here's a new design, a completed clapper for a very large bell, and it has 4 different hardnesses. Here's soft, indicated by S. Here's medium, indicated by the M. Here's medium hard, indicated by MH, and here's hard. So all these felts are of a different density, and then will produce a different tonal quality when when the bell struck. Now over here, these ladies are putting together clappers. And here is a part that we'll see in a little while, shortly. This is the yoke handle, as we call it, coupler. And the yoke, which is this black part, will be assembled over this. And there'll be 2 bearing screws installed in the sides, and it's the bottom part of the clapper. Clapper head goes on here, and it'll pivot here. And she's just putting the bearing screws into one of them, just as I just described. There's a great deal of handwork here, all the way through the handbell operation, actually. And this lady is assembling a restraining spring right now to a spring plate at the bottom, just below the yoke. Now, let me demonstrate that for a second, will you? Now, there, she's got it assembled, and she's drawn a screw down which pulls the ends up. Now, notice if I were to swing the clapper this way in a bell, it will contact that spring and it will deflect the spring downward. You notice that? That permits it to go on and strike the inside of the bell. There's the action, and then holds it back away from the bell, allowing the bell to vibrate. If we didn't have that spring on it, would strike the bell and lay against the bell and kill the vibrations. Thank you. Now, in these bins up here, there are completed clappers of all the different sizes that we use in all the different notes of bells. Down in here are additional parts in these bins. And over there, there's an overflow of completed clappers on that table.
I am going to jump ahead to handles because we are running out of time. You all can come visit us here at Malmark and see our chime manufacturing. Okay.
Handle, so that part of the handle is going to be softened by the heat. And then when she gets it out on this side, she's going to take and form it over the appropriate form. Now she's got that one, and look at the size of the bigger one, so you can see that we have a number of them. And she's going to just wrap it quickly around there. Going to give it a quick chill now in cold water. Chills the surface, and then she's going to put it into these holding racks, one of them. And that is how they're left for about 24 hours, and this is what the result is. And from that point, there are 2 holes punched in each side of the handle strap, and then they are assembled as this lady is doing here, with 2 screws on each side, with a handle block, which is this thing, in between. And then later on, with that strap on here. Then there's a main assembly screw, as I described earlier, that goes through and fastens it through into the bell, through the bell and into the clapper assembly. The note designations on the handles. You notice she's slipping one in now. There's nothing on it, it's bare. This heated platen comes down and transfers this printed information, which is on a plastic tape, and the heat and the pressure transfers it over onto the handle, permanently bonding it there. And that's the part that goes inside the tube. We're now in the choir chime department.
So I know I'm out of time, so I should probably leave a little room for questions. The last bit of the video was going back to our back building. We have 2 buildings here at Malmark. In our front building are our offices and where we do all of our bronze work. However, we then are separated by a warehouse in between, and then we have a back building where we manufacture choir chimes and aluminum bells. The 2 buildings have to be separate. The HVAC has to be separate because we could never cut any aluminum around the bronze chips because that would contaminate them, and then we wouldn't be able to recycle them. So I'm so sorry I went over time, but I'm happy to take any questions. If you have to leave, I understand as well.
I've got some questions from the chat, Kathy.
Okay.
Does the Malmark manufacturing area, does it still look the same today as it does?
It does. I would say probably back in 1997. You know, I feel, I don't think I'm speaking out of turn here when I say the peak of handbells was right around 9/11. I think, you know, for HMA, for the Guild, for their membership, and for handbell sales. So we probably had 75 employees back in 1997, and today we have 30. Some of that is a product of COVID. Because obviously sales haven't been so good for the past 16 months. And so we're all running furloughed 1 day a week so that no one had to lose their job. We just all gave up 20% of our salary. So that's how we're running right now.
And why is the Malmark on the inside, why is it smooth polished as compared to the inside of the Showmerk bells?
Basically, it was just one more step to take. We complete the tuning on the inside. And so Mr. Malta just decided that he wanted to polish out the machining lines so that it would be easier to keep the inside of the casting clean.
And who makes the other parts of the bell for you guys, like the handles and the clappers and the?
Well, you saw that the handles are assembled with an extrusion and then the nylon straps. So we have suppliers that send in the blank straps and the extrusions that are cut. Mr. Malta always used to say we would do everything here in this building that we could if we could do it for less expensively than a vendor could, knowing that our customer base, Malmark was a little peculiar in that we never went into tower bells. So we didn't have that. We only have done handbells and choir chimes. And then after Mr. Malta passed away, got into cajones a little bit there for a while. So we had to do everything we could to keep our quality up and our costs down because most of our customers are not-for-profits.
And you've already talked about the number of employees you've got now. How many are in the manufacturing side and how many are in the office side?
In the office, we have purchasing, me. We have right now we have 6 in the office.
And what happens to the rejected castings? Are they melted down to recycle or do y'all hang on to those?
We have since that time in the video, Mr. Malta held on to everything. He had hundreds and hundreds and hundreds of barrels of reject castings, but we have since, when you melt those castings down, you get $1.25 a pound. So you just saw the hours that were put into machining, to polishing, to voicing. And so there's only so many gift bells that you can sell. So we do sell them as scrap. We sell them back now in these leaner times.
Right, exactly. And somebody had asked, they thought, did Jake design most of all of the equipment that's used?
He did. He designed the equipment, as well as, like that cradle that holds the bell while it's turning in the lathe. He called that flying fingers. So it was holding the bell so that it wouldn't rock back and forth, so that the casting wouldn't be lathed crookedly. So he designed that whole harness there. But just the whole manufacturing procedures and the fact that we don't use a coolant, he did it all. He was brilliant.
That was all that I had in the chat. Is there anybody else that has a last minute question? You're welcome to add it to the chat or ask it in person.
Linda.
All right, Miss Linda.
Trying to find my unmute button. So tell me where you do, when we send something back to be refurbished, where does that go in that process?
It goes in the room where they were assembling the bells, and that's called our final assembly room. So in that room where they were assembling all the bells, they first of all will disassemble all the bells, and then the handles go over to the handle department, the clappers go over to the clapper department, the castings go back to the polishing room where they are machine polished. And then when everything all reassembles in final assembly, then your bells go into the voicing room. So literally the same people who make the handbells are refurbishing them for you. Same standards. And there are different levels of service. I really am proud of the fact that we do tonal work on your bells. We're just not cleaning them. We're just not adjusting the clapper assemblies. I like to use the analogy. It's kind of, if you don't have the tonal work done, if you don't have the revoicing done, or, give us the opportunity to say, oh, this bell is bad and it's covered by warranty, we'll replace it for you at no charge. I equate it to hiring a piano tuner who comes in and cleans the keys and polishes the wood, but never listens to the piano. I think sometimes handbell musicians forget that these are musical instruments, and it's important. The sound quality is important. I'm on Facebook like many of you, and I cringe sometimes when I see the little wars going on for a used set of bells without ever hearing them. A lot can affect the sound of the bells.
All right, we've got two questions that probably can be combined together. Is the process for manufacturing the aluminum bells similar to the bronze bells?
It is. It's very much the same, except Carolyn, the lathes are Texas size. The larger the casting, the larger the lathes have to get. And that happens in the back room. And I apologize that we ran out of time there. But it's the same exact process. Just everything is supersized. And
I can't remember if you mentioned this. You said the chimes are made in the same building as the aluminum?
Because they're both aluminum, and aluminum being soft it creates a lot of dust, a lot of smoke, and it would contaminate the bronze chips.
Well, lots of good questions. Thank you, Kathy, for joining us tonight. This is wonderful.
May I just mention, because we don't have the Foundry here, but if you go on YouTube and Google how it's made handbells, the show from the Discovery Channel filmed here at Malmark, but they also went to our Foundry. So it's it's great to see how it works at the Foundry. So again, the show is called How It's Made, Handbells, and you should be able to find it on YouTube.
Perfect. Well, thank you so much for joining us. This has been great. For those of you that joined us tonight, we have 2 more roundtables on June the 21st, which is going to be the history of bells. And July the 5th, we're gonna be with Chilmerick that night. So we hope y'all can join us for the last 2. So that's June the 21st and July the 5th. And we will see you soon. Thank you again, Kathy.
Thank you all for joining us. Come visit us in person.